In this lecture, we are going to talk about the memory interface of the 8086 microprocessor. And so we can say, what is an interface? What does interface mean? It means, when you want to establish a communication or establish a path to communicate one device to another one, or establishing or making connection between two devices or two components. In order to make connection between them, between two or more than two devices, you need to have an interface. You need to connect them together. So this interface means, making a connection or connecting two or more components together. And in this case, we are going to talk about the microprocessor and the memory interface. That means we are only interfacing the 8086 microprocessor to the memory, or the memory to the microprocessor. Why do we need to interface the microprocessor to the memory, or connect the memory to the microprocessor? Because whenever the microprocessor executes an instruction, it needs to access the memory. It needs to access a memory location or more than a memory location in order to fetch that instruction, or to fetch those data which are going to be manipulated by the already fetched instruction. So in order to do this, both the microprocessor and the memory must be connected together, or in order to establish this connection, they require some signals. Okay, so there must be some signals that the microprocessor tells the memory which operation to be done, or some signals which can be gone from the memory to the microprocessor, such as sending data or receiving data by the microprocessor from the memory location. And the interface process includes some key factors, and those key factors tells whether the memory can be interfaced with this microprocessor. So they must match together. The memory must meet the requirements which are required or requested by the microprocessor. Then it can be interfaced with the microprocessor. And the 8086 microprocessor itself is a 16 bits microprocessor. That means the size of the internal registers of the 8086 microprocessor are 16 bits, and it also has 16 bits data bus. That means through these 16 bits, data can be sent to the memory, or they can be received. And even this microprocessor has the ability to access 1 megabyte of memory. That means the number of the address buses is 20 bits. That means through those 20 bits, the microprocessor can access a memory which its size or its capacity is 1 megabyte. And this microprocessor housed in a 40 pins dual in line package. That means the block diagram of microprocessor is consisting of 40 pins. Through these 40 pins, the microprocessor can be connected to the additional circuits or additional peripherals, such as memory or the clock, or sending signal to input or output devices, or whatever. So the whole microprocessor is consists of 40 pins. And we know that every microprocessor must have a memory interfaced with, and each memory device must have some signals or some lines or some connection pins in order to be able to communicate with the microprocessor. And they are address connections, which through the address lines, the locations of this memory can be selected by the microprocessor. The individual memory locations can be selected by the microprocessor, which sends this address through the address line. And some of them are called the control connections. So it controls the operation of the memory, whether the microprocessor reads a data from this memory or writes the data to this memory. And the data bus, which can be used in order to insert a data to the memory location or get a data from a memory location. And we've got a chip select as well, in case whenever we have more than one memory more than one memory established in a computer system. So this chip must be available in order for the microprocessor to select a memory location or to select one of the memory locations at any given time. It can be said that the 8086 microprocessor can be working on two modes, and they are minimum mode and maximum mode. And the minimum mode is used when the microprocessor is working in a single processing environment, or when only a single processor is inside the computer, or only one microprocessor performs all the tasks inside that computing system. And the maximum mode is used whenever we've got more than one microprocessor inside a computing system, and this can be done by applying the logic 1 to this pin, which is min max pin. If you are applying logic 1 on this pin, that means the microprocessor is working in minimum mode, which is single processing environment. And whenever we are applying logic 0 on this pin, the microprocessor is working in the maximum mode, and that means it is a multiprocessor system. And depending on those modes, whether it is a minimum mode or maximum mode, some pins or the function of some pins is going to be changed inside the microprocessor. Those signal pins or those functions are common in both cases, in both modes. For example, address data bus from pin number 0 up to number 7, they are working as the same functionality in both cases, and those pins as well. But here we have those pins which are unique to minimum mode signal. That means whenever the microprocessor is working in minimum mode, those pins are performing those kind of functions. But those pins are going to be changed whenever we are using the computing system at the maximum mode, in the maximum mode. For example, RQ GT01, and they are using to request grand bus in order whenever the other microprocessor tells this microprocessor to release the system bus, and those kind of things, log and those status pins, and another instruction queue status, and those pins are used whenever the microprocessor is working in the maximum mode. So the minimum mode interface signals. In minimum mode, the microprocessor itself, the 8086 microprocessor, provides every signal in order to be interfaced with the memory or the I/O devices. So it interfaces with the memory and the I/O devices by itself. It doesn't need any additional circuit. And in this mode, the signals which are used in order to interface with the memory are address and data buses and status signals, control signals, interrupt signals, and DMA, direct memory access signals. And we are going to talk about them one by one. So at the beginning, let's see what is the block diagram, what is going to happen in the block diagram of the minimum mode 8086 microprocessor. You see those are the control signals, ALE, bus high enabled, or memory I/O selection, data transmit, receive, and the read, write, and data bus enabled or ready. And those are called the control signals, and these are the address and data buses. As we know that from the address data, the number of the bits of the address bus are 20 bits, so those 16 bits and those 4 pins are used, and these are called the interrupt interface, interrupt request, interrupt acknowledgement, non-maskable interrupt, test, or reset. And these are used as the direct memory access interface. For example, whenever the devices are requesting the microprocessor to release the buses in order to be used by them, the microprocessor is sending an acknowledgement signal through this pin. And those are the power supply, VCC, and ground. And through this pin, the microprocessor can be selected to work either in the minimum mode or in the maximum mode operations. So the address and data bus pins, and those pins are 20 pins, while the 20 bits are used in order to hold the address for the memory location, and only 15 of them are used as the data bus. And whenever the microprocessor accessing the I/O device, it uses only 16 bits. Why? Because the maximum size of the I/O device are going to be 64 kilobytes, and we say that the data bus pins are 16 pins, and they are the pin number D0 up to D15, and we know that those pins AD0 and up to AD15 are bidirectional multiplex. That means they can transfer or receive information, and even they can be used to dual purposes, which are address whenever we are using those pins as accessing the memory location, or specifying a memory location on those pins, and whenever they are holding a data, they are used as the data buses. And the status signals are those signals which are multiplexed with those pins from A16 up to A19, which are 4 pins or 4 bits, and they are from S3, S4, S5 to S6. They are 4 status pins. So they are used for special purposes. For example, S3 and S4 indicates that which internal segment register used in order to generate the physical address. For example, if they are 00, that means in the current access of the memory, the extra segment register is used, and for example 11, the data segment is used, while the S6 is always logic 0, and the S5 indicates the condition of the interrupt flag. That means if interrupt flag is 0, that means which we have disabled in the interrupt, this pin is going to be 0 as well, and if it is 1, this one is going to be 1. And the control signals provide the support of the interface from the microprocessor to the memory and the I/O devices, and the functions are, for example, whenever we have a write address on the address bus, then through these control signals the microprocessor knows in which direction the data is going to be transferred, or whether the data is going to be read from the memory, or the microprocessor wants to write a data to the memory. And the pins are memory I/O. This pin is used whenever the microprocessor wants to communicate with the memory or the I/O devices. If it is 1, that means it is communicating with the memory. If it is 0, it is communicating with the I/O devices, or that means through this pin the microprocessor can select a memory or an I/O device, data transmit or receive. So through this pin we can know in which direction the data is transferred. Is it transferred from the microprocessor to the memory, or it is received from the memory to the microprocessor? Read. This pin indicates that the microprocessor is performing a read operation. This one, the microprocessor performs a write operation. And ALE, address latch enabled. Through this pin we can know that the microprocessor or the buses of the microprocessor are used as the address bus or the data bus. When it is 1, address latch enabled, that means the microprocessor or the lines or the buses of the microprocessor contains address. When it becomes 0, so that means the data are on site, those multiplexed bidirectional buses. Data enable is a pin that enables the external devices to supply data to the microprocessor. When it is logic 0, it is active low. So whenever this one is active, that means the data bus is enabled, so it lets the external devices to put some data on those data buses in order to be transferred to the memory. And the ready is used, for example, we know that the speed of the external devices or peripheral devices are much times slower than the speed of the microprocessor. So this pin is used whenever the external devices or the memory devices, I/O devices, are ready to complete their operation with the microprocessor. So when they become ready, they send a signal through this pin to the microprocessor to let the microprocessor know that they are ready, so the microprocessor transfers its control to them. It's going to execute those instructions which are relating to those external devices. Bus high enabled or bank high enabled, that means whenever this pin is active, which is active low, and so it tells the addition or the external circuits that whether the transfer is taking place on the upper 8 data bus lines or lower 8 data bus lines. So when it is 0, that means those data which are transferred are on the upper 8 data bus lines or upper 8 data bus bits. But when it is 1, that means the lower 8 bits of the data bus are used in order to hold the data. And the interrupt signals are some signals which can be used whenever the external circuits wants to take the control of the microprocessor, or they want to be served by the microprocessor. One of them is the interrupt request. This pin is used whenever an active peripheral device wants to send a signal to the microprocessor in order to let the microprocessor know that this external device wants to be served. So this pin is going to be active whenever it is logic 1. But when this microprocessor recognizes this interrupt, or the microprocessor detects there is an interrupt over this pin, it's going to respond to this peripheral device through the interrupt acknowledgement pin, which is an output active low signal. Then when this happens, that means the microprocessor is going to serve that external device which has already sent the request to the microprocessor. So, and every time the microprocessor is checking those pins, the interrupt request and this pin, non-maskable interrupt, which is the same as this one but a little bit different, and I'm going to talk about them. The microprocessor checks those pins periodically. So this one is non-maskable interrupt. It is used in order to let the microprocessor know that an external device has generated a request to the microprocessor in order to be served, but this one is not going to be masked. Whenever this happens, whenever this pin is logic 1, the microprocessor must respond to it, must suspend the execution of the current instruction and takes the control of that to that external device which has sent the interrupt signal through this pin. So this one is the same as interrupt request but with highest priority, which cannot be masked. Okay. And the direct memory access interface signals, whenever the external devices wants to use the system bus or the data buses of the microprocessor in order to communicate with the memories, they are sending a signal through hold pin, which is going to be active whenever it is 1. When the microprocessor sees that one, after the completion of the current cycle, it sends another signal to that external device through this pin, hold acknowledgement pin, in order to let the external device know that they can use the system buses right now. And let's talk about the maximum mode of the 8086 microprocessor. The 8088 or the 8086 microprocessors can be used as the minimum mode and the maximum mode. So when they are used at the maximum mode, that means these microprocessors are working with the other cooperating microprocessors. So that means there are more than one microprocessor inside this computing system. So, and each microprocessor in those computing systems is dedicated to perform some function. Each of them is assigned to perform a program or to execute a program, and there are some resources inside this multiprocessing environment. Some of them are called global resources and some of them are called local resources. So the global resources are those resources which can be used by all the microprocessors, and they are common to all the microprocessors. They are available to every single microprocessor inside that computing system. But whenever a resource is called a local or a private resource. That means it is assigned to a specific microprocessor, or it is dedicated to a specific microprocessor, and it can't be used by the other microprocessors. And in the maximum mode operation of the 8086 microprocessor, the control signals are not directly interfaced or connected with the memory. So instead, they are going to be provided through those three pins, those status codes pins S0, S1, S2, which are active low. So, and they are going to be input to an additional circuit which is called 8288, in order to decode those bits to a right operation, or to that operation which has been specified by the microprocessor. For example, if they are 000, that means this microprocessor is performing interrupt acknowledgement to the external device. Or when they are, for example, 001, that means the microprocessor is fetching an instruction from the memory. And for example, if 010, that means the microprocessor is performing a write operation to the output devices. Or when they are 111, in this case we don't have any operation, that means the microprocessor doesn't perform any operation with the external devices. And there are three other pins which is going to be provided by the 8288 a device, which are data enable and data transmit and receive, and the ALE, which are all performing the same functions as we were talking about in the minimum mode operation of the 8086 microprocessor. And this block diagram shows when the microprocessor or the 8086 microprocessor is working as the maximum mode. So this is the 8288 bus controller, which is working as a decoder, which decodes those operations or those pins which coming from the microprocessor to the input of the bus controller S0, S1, S2, and this one, this 8288 bus controller decodes those pins to those outputs. So in each case, one of them is going to be available, and we said that those pins are performing the same functionality as they were doing whenever the microprocessor was working in the minimum mode. And those are the address and the data lines and block bus high enable. They are performing the some functionality, or they are common in both cases. They are used for the same functionality whenever the microprocessor is configured in the minimum mode or in the maximum mode. And those pins which are used, for example, whenever the other microprocessor wants to control the buses, they are going to send a request through this pin to that microprocessor which is already using the buses. So through this pin, the microprocessor which has the buses is going to send back a signal or an acknowledgement signal or a grant signal to that microprocessor, in order to let the microprocessor know that it can use the system buses right now. And we have the log signal in case the microprocessor is configured in the maximum mode, and it is used, or it is provided by the 8086 microprocessor in order to let the other microprocessors know that they can't request the system buses or the shared resources which is being given to this microprocessor right now. So it logs everything so that the other microprocessors can't request those kind of resources which is been given to this microprocessor, or which is been working with this microprocessor right now. And the system clock of the 8086 microprocessor is being given by this device, which is called 8284 clock generator, which generates a clock pulse to the 8086 microprocessor. So this microprocessor is working or performing each cycle based on that clock pulse which is being sending from this 8284 clock generator. A bus cycle and the timing states of the 8086 microprocessor. A bus cycle defines that operation which is being performed by the microprocessor with the external device such as memory or the input or output devices, and those operations are memory read, memory write, IO read, and IO write. So in each time when the microprocessor performs an operation, the bus or the bus cycle is going to be consisting of 4 clock periods, and they are called T1, T2, T3, and T4. So during the T1, the microprocessor is holding an address. Okay, so the buses of the microprocessor are holding the address which is going to the memory or going to the input or output devices. We know that those lines or those buses are multiplexed bidirectional. Whenever we say they are multiplexed, that means they can be used for dual purposes. So in 8086 microprocessor, they are used whether to hold a data or to hold an address. So during T1, those buses are used in order to hold the addresses. So when the microprocessor performs a write memory cycle, those data which are going to be written to the memory location are going to be put on the data buses during the T2 and maintained through T3 and T4. So through the T1, the microprocessor the buses are holding the address, and for the write operation, those buses are holding data through T1 and T3 and T4. But for the read memory cycle, or when the microprocessor performs a read operation, and we know that for every cycle during the first time or the T1, the microprocessor holds an address. But for the read memory cycle, during the T2, it is in the high impedance. That means it doesn't do anything. But during the remaining cycles, which are remaining time periods, which are T3 and T4, the data must be available there. The data is going to be put on the data buses. So during the bus cycle, some status may happen. Some of them are idle and wait status. And idle state is when the microprocessor doesn't do anything in that cycle, which is called an idle cycle. So it's going to remain for one cycle period long. That means all the T4s or T1, T2, and T3 and T4 are going to be idle. So even during any operation, there may be more than one idle state inside the bus cycle of the microprocessor. And we also have the wait state. These wait state can be inserted inside a bus cycle, not between two bus cycles. And this is being done by the external devices. When they are not ready, the microprocessor must be waiting for them. So in this time, when the microprocessor is waiting for the external devices to be ready, is called a wait state or a waiting state. So the ready input of the 8086 microprocessor is provided for this purpose. When the external devices are going to be ready, they are going to send a signal to the microprocessor through this pin in order to let the microprocessor know that they are ready to be served, or they are ready to be working with the microprocessor. And this is a normal bus cycle: T1, T2, T3, T4, which is one bus cycle. T1, T2, T3, T4, another bus cycle. Here we've got T1 up to T4, a bus cycle. Here we have got another bus cycle. But look here, this is called an idle state. We've got T1, T1, T1. So they are called idle clock cycles. The microprocessor doesn't perform anything with the input or output or the memory device at this time. And we know that each bus cycle is consisting of 4 times. During the first time, holding an address and the data for the remaining parts. But it comes to some cases that the microprocessor or the memory or the input output devices are not ready to be served by the microprocessor or to communicate with the microprocessor. So at this time, the microprocessor goes to wait state, which is called wait state of the microprocessor. And the bus cycle is going to be extended to 4 times or more than 4 times anytime when the input or output or the memory devices are going to be ready. Let's see the hardware organization of the memory address space, or the memory of the 8086 microprocessor. And we know that the microprocessor or the 8086 microprocessor's memory is 1 megabyte. This megabyte is divided into 2 parts. They are called low bank and the high bank, and each bank is 512 kilobytes of data. And the low banks are holding the even addresses, the high bank are holding the odd address. That means from location number 0 up to FFFE, and this one 1 up to this one, only including the odd memory location, and this one only including the even memory locations. So for the microprocessor to access any memory location, it must have those inputs, which are 20-bit address bus, and the address buses are pin or the address lines are pin A0 up to A19, which are 20 bits and bus high enabled. So we know that through those 20 pins we can access any memory location, but these pins are used to access the memory location, while this one specifies whether the location is going to be in the high bank or in the odd bank. When it is 0, that means it accesses the even bank or the odd bank. When it is 0, that means it is accessing the even addresses. That for example, if the least significant bit of any number is 0, that means that number is even. But whenever it is 1, this pin is 1, that means it is accessing the odd address locations. And bus high enabled, it enables the high bank. Why? Because every time whenever the microprocessor accessing the high bank of the memory location or the high bank memory locations, the data of them are going to be stored in the higher part of the address bus. And we know that the data can be input to the microprocessor and output from the microprocessor, and we know that they are 16 bits, D0 up to D15. The D0 up to D7, which is the lower byte of the data bus, are used in order to hold the even addresses, and we know that each address is holding 1 byte of data. And the D8 up to D15, which is the higher byte of the system bus, are used in order to hold the odd address. Let's see that example. And this can be the memory of the 8086 microprocessor, which is consisting of the high bank and the low bank. Each of them is 512 kilobyte, and through the 20 bits address bus, or we can say the 19 of them through A1 up to A19 are going to be connected to both banks, while the A0 is going to be connected to this one. Whenever it is 0, this one is going to be activated. But when the bus high enabled is 0, that means when it is active, this one is going to be activated, or when this one is 1, this one is going to be activated. So these are the lower bank, these are the higher bank locations, and the data of them are going to be placed on those bits up to D0 to D7 on the data bus, but the data of them are going to be held on those bits D8 up to D15. For example, if you want to access an even address byte, okay, only 1 byte but in the even address, so through A1 up to A19 we can generate the address, and A0 as well. A0 must be 0 in order to access the any location of the even bank of the 8086 memory, and the data of that location, which is in the even bank or in the lower bank, is going to be held from those 8 bits or the lower 8 bits of the data bus. And in this case we are not accessing any location of the higher bank, so the bus high enabled is going to be high, which is going to be deactivated. Why? Because this pin is active low. It is active when it is logic low or logic 0, but at this time it is high. And when we are accessing an odd address, so what happens through those pins which we can generate the address, and the A naught must be 1. If it is 0, this one is going to be activated, but the 1, this is not going to be activated, so the bus high enable is going to be low, so this one is going to be activated, and through this one we can access that location, and the data of it is going to be held inside those pins. We said that the bus high enabled, the higher part of the bus is going to be enabled, so A naught is 1, so this one is activated. But whenever we want to access 16 bits of data, so we know that whenever the microprocessor can't access 16 bits of data directly, it can access 8 bits, so the next 8 bit is going to be padding with this one in order to form a 16 bits up. So whenever it accesses this memory location, which is an even address, so the I naught must be A naught must be low, so the data of it is going to be held on those data lines, and the next time the bus high enable is going to be low in order to enable the higher part of the data bus, and the data of it are going to be stored or are going to be held on those memory locations, those data bus pins from the D8 up to D15. And this example explains the way the microprocessor accesses the memory locations in more detail. For example, we are accessing an odd address for 16 bits of data, so those pins with this one are holding the address. As we said, this one tells whether the location is inside the lower bank or the higher bank. So we are accessing an odd address, which if the data inside it is x plus 1, for example, and in this case the A naught must be 1. Why? Because those are the odd addresses, and the A1 must be 1 in order to generate an odd address, and we need to make the bus high enable active, so you can activate it by putting logic low inside on it, and the data of it are going to be stored or are going to be held on those data pins D8 up to D15. And we just got 8 bits of data, but we need a word, that means 16 bits of data, so the next data is going to be the next memory location. For example, if it is 17, this memory location is 17, this one is going to be 19, so we are accessing that. In order to access that, the next memory location is going to be accessed, and this one was high, so it's going to be low. Whenever it's going to be low, this memory bank is going to be activated, and the data of it is going to be held on those data bus lines D0 up to D7, and the bus high enabled is going to be high in order to activate the higher or the upper byte of the data bus.